Okay, as I committed, I will show you the code how it runs. So we are solving ordinary differential equation using finite difference methods. Look, we have this directory boundary value problem where we will be only running this man file script. And these two commands clears our screen and clears memory. We are for time being solving this differential equation with these boundary conditions, and general form which is being used in this code for a second order linear or nonlinear ODE is this one: y double prime is equal to py prime plus qy plus r. R is a merely function of x or only function of x. P and q are also functions of x, so it makes it linear or maybe quasi-linear. So p and q do not depend upon y. And mention, it's important to mention that p, q, and r should be provided as a separate function, right, of x. So first of all, this p, looking at this differential equation, p is -2. It's a -2 constant function. So we have created a separate function p which takes input x and simply provides -2. If you want to, describe or have if you have another OD where p is different, so you will adopt this function. Similarly, q, look at this general OD again. Q is -1, minus because this will be on the right hand side, shifted to the right hand side according to this formulation. So q is -1. Now look at this, so it is simply a -1. And next is x square, which is r. So r is same function which takes input x and gives you output as x square, right? And next is these are now this is main file where you will have to use simple one file, ODE, one function file, ODE boundary value problem. So you use this syntax to call this function. Here it is being called, and it wants to, or it will take input as a, let's say, 3, 4, 5, 6, 7, 8 inputs. And if you want to know about all these inputs, just go to this file and see. PQR are coefficient functions, A and B the endpoints of the interval, GA and GB the prescribed functions values are boundary conditions, the value of boundary condition at the endpoints. Okay, and the number of subintervals, now outputs. So this was all about input, and now output Z. Z is a matrix where one column is solution. So one column is base points x, and second column of the matrix is solution, so y at those base points. So this is ODEP, and inside this function another function is being used which is tridiagonal. So it solves the linear system, the matrix equation being formulated after using these finite differences, right? I'm not going to dig into this tridiagonal function because it's kind of black box for you. So we will only play around this one. So in order to call this function, we will have to pass on these 8 inputs. So a and b are the endpoints of the interval 0 and 1. Value of function or solution at endpoint is 0.2 to 0 and 0.8 respectively, g and gb. N is the number of points, which is 4. Time being, as we have seen that it is done with n is equal to 4 in the presentation. So we have used the same problem, same ODE, which is already solved in the presentation, just to verify or validate that our code is running well. Okay, and PQR are 3 different functions, coefficient functions. They are defined in these separate files. I hope you can see this one, right? And next, this will give us this Z matrix which contains 2 columns. One is values of base points x, and another one is solution of x. Now, let me run this code and see if Z is really that one. So this is Z here, and I just comment all the other things which I'm going to explain in next couple of minutes. So I have commented all this stuff, and only I have Z here, clear all. CLC will clear the memory and clear the screen. So how I can run this one, and going into the editor on the top, if you are running, using Octave, so this will work also on Octave in the same way. So just to run this, you see the screen was once cleared, and then we have Z on the screen. So this is X and this is Y. So this is what Z output is given by this function. Now our next phase is to plot and display this solution stuff. So I'm decommenting this, and I'm removing this Z here and saving this function. And now plotting phase. So first of all, in order to compare the solution obtained from this finite difference method, we must have exact solution. So exact solution for this particular PD is, or D is this one, which was solved by some online tool, let's say. See, right? So this is a function which defines exact solution at x 1 by 5 times all this stuff. So yx is a function handle which handles this solution function. So if I give x, which is starting from a and ends at b with a step size of this h, b minus a times n. Okay, so look at this, what x is. I copy this and I paste it here, enter. So it is 0, 0.2, 0.5, 0.75, and 1. So this is x. Now when I give this x input to this function handle yx, so this yx is a function handle. When I give input to this function handle, I get, okay, so first I have to run this one, right? So Control C, and now this is function handle, and clear screen once, yx, give input, and now we have values of y, so exact values at these 5 points, and these are being stored into the variable y. Okay, now for sake of plotting, open the figure handle, empty figure. So plot x on the x-axis, y this exact solution with a red label. Okay, hold on, plot z this matrix Z. The first column was values of x, so this is first column, this is second column, values of y, and this is blue line, right? Blue line, and this is red line. Okay, so legend, exact and finite difference method, and title of solution comparison. These are some fancy things about the figure. Hold off. So this will plot our figure, and next we want to display our computed solution in the exact solution. So Z already had, so x and computed solution, so this y transpose will be transport of this exact solution. So displaying this will give us y computed y exact against the x. So let's run this complete code. So it's not saved. When I will run, it will save and run. Okay, and first of all, figure, the red line is exact and the blue one is finite difference method. Okay, and this is what, let me run it again. This is figure, and this is how we can see the graphs. Oh, sorry, not graphs, but the solution in form of tables. So this is these are values of x, these are values of y computed, and these are values of y exact, right? Now, in the end, I like to put a question, and that is why this computed solution is different from the one presented in the presentation. So what is the reason? And I give you a hint to sort out this question is you have to see the formulation in the book from where we have got this code. Thank you very much. Looking forward to your answers.